Okay, we're going to analyze this schematic drawing for a ship's mast, and what we're going to do is look at it and analyze it as a truss. The best way to start analyzing a truss is to look at a point you know enough about that you can actually find out the compression and tension members. So we're going to start by looking at point A up top here. So we have an external force acting, and that's going to have to be resisted by these two members here. And in fact, because axial forces, tension and compression, can't go around right angles, we know straight off there's going to have to be a horizontal force from this diagonal member resisting the external force. But because the diagonal member does not go straight horizontally, this force here is going to have to be made up of a horizontal component, already drawn, and a vertical component, like that. And this total force should resist the external force, drawn in blue, but we've also got a leftover out of balance force here, the vertical component of the tension in the diagonal member. But this force can also be resisted by the vertical member going into compression, providing an upwards reaction force. And altogether, this means we have complete equilibrium. So the node should look something like this, with tension in the diagonal and compression in the vertical member. So let's move on to node E, which is going to look something like this. And we already know we have a tension force here, which, just like before, is going to have to be split up into vertical and horizontal components. And just as before, we know axial forces can't go around corners, or not right angle corners anyway. So this vertical force here will have to be resisted by this lower diagonal. There we go. And because that's not completely vertical, that member, to create a force that's going down the member, it needs two components, one horizontal and one vertical, like that, to add up to the total force. So vertical equilibrium is satisfied, but because this diagram is getting a bit confusing, let's just look at the horizontal forces. We can see these two forces are acting in opposite directions to each other, and to work out qualitatively which one's bigger, we need to have a look at directions of the two members. This one here and this one here. And you can see that this member here is kind of more horizontal than this member here. And because they both have the same vertical component of force, our first member, this top member, is going to be applying more horizontal force at the node, just because it's facing more horizontally. And there is maths that will back this up for those of you who can do trigonometry, but to get an intuitive understanding, that's about as far as you need to go. So because this horizontal force is bigger than this one, at the moment we're out of balance by a net force going in this direction, which, to put the whole node into equilibrium, must be resisted by compression here in the horizontal member. And that's E all done with. Got tension here, and compression here. Looking back at the structure, we can start to fill things in. So tension, compression, and it's much the same story going all the way down. Got tension in all the cables, compression in the column and in the yards. And you can go through the analysis of each of these nodes if you want, but as long as you understand
how the principle works, then you should be fine.